In this video, we're going to look at what happens when we encounter one or two special kind of trig limits that we often see in these kinds of problems. Now, whenever we're given a limit problem in general to deal with, the first thing we want to ask ourselves is, can we plug in the value that we're approaching into our function to figure out what our limit is? If so, we don't have to worry about all these special trig limits and all these special rules. We found our limit. So let's go ahead and come up here and do some quick little plugging in and kind of seeing what we get here. So we're going to plug in 0 for t and see what we get. So we get 0 minus 0 cosine of 11 times 0, or 0, over sine squared of 0. Sine squared of 0 is just sine of 0 squared, right? So sine of 0 is 0, 0 squared is 0, and then we get 0 minus 0 times cosine of 0. This becomes 1, but 0 times 1 is 0, so 0 minus 0 is 0, and we get an indeterminate form. When we get one of these indeterminate forms, namely 0 over 0, maybe an infinity over an infinity, infinity minus infinity, something like that, even though infinity is not seen as a number, it's seen as an expression of going on forever and ever, because you can't use infinity to describe infinity. Anyways, when you get one of those forms, you have to do some algebraic and some other type of calculus manipulations in order to solve these limit problems and make your limit more apparent as to what it is. So let's start that process by taking care of our numerator, in a sense, by factoring a t out of both of the terms in the numerator. Okay, so we change this to limit of t approaching 0, t times 1 minus cosine of 11t, like this. And what we're also going to do in the same step here is we're going to take this function here and break the numerator into one fraction like we did here, and multiply it by another fraction that contains the denominator of our original. It just makes it a little bit more easy to deal with as we move into these problems here. So what we did was we factored a t out of this first numerator here, and then split the numerator and denominator into their own respective fractions. After we get here, what we're going to utilize is the fact that in the real numbers, multiplication commutes. So we have this going across the top. We have t times this expression 1 minus cosine 11t times 1. We're going to change the order around a little bit just to help us with some notation here. So we're going to rewrite almost everything the exact same, except when we get here, we're going to leave this on the top, times 1, times, we're going to bring the t over here. So we did t times 1 gives us t over here, and we get this. So we have all that good business going on, right? So don't be alarmed by the fact that I brought in the other limit down there. I forgot that I would need it in this problem a little bit to kind of help us out later on, but we're going to go ahead and move on. When we use these types of results, what we need to make sure that we can do is we want to make sure that the argument of our trig function that we're looking at, that argument is also repeated in the other half of the fraction that we're analyzing. Okay, so namely, since the 11t here is the argument of cosine in the numerator, we see that it has to match what's in the denominator. And all we have down there is just a 1, right? So in order to bring in the 11t into our denominator, I'm also going to have to bring it into our numerator of our fraction through use of multiplication. So how I'm going to do that is I'm going to multiply the product that we have inside of here by a special version of the number 1, namely 11t over 11t. All we're doing is we're multiplying this by a very specific form of 1. And the reason we do that is, again, multiplication's commutative, right? So the order doesn't matter. Here on the bottom we have 1 times sine squared of 3t times 11t. Let's go ahead and take this whole 11t right here and bring it into the denominator of our first fraction. Okay? What I'm also going to do is I'm going to bring this t into the numerator of our second fraction. Okay? And I'm going to bring those in and do a little bit of manipulation to help us see what we're doing with our limits. So let's rewrite everything that we've just talked about and done. So we have 1 minus cosine of 11t over now 11t times t squared over sine squared of 3t, right? And we're not going to forget that we have this 11 sitting out here. what we did in our original multiplication there. So now what happens here is we view 11 as a constant multiple of this limit, right? Because there's no variable that we're approaching or evaluating as we approach closer to, right? So we view this 11 as a constant. We really don't have to pay this any mind until we get to some of the last steps of our process here. What we're going to take care of now is we're going to say, since we're taking the limit of a product, we know by the product law for limits that as long as these limits exist individually, we can take their product of their limits to give us the limit of the original function, right? So we're going to say, as long as these limits exist, we can follow it up with this next step here. We can do 1 minus cosine 11t over 11t times the limit as t approaches 0 of t squared over sine squared of 3t. Okay, and let's not forget that we have this 11 out there. Let's go ahead and bring that down. So what we did here, going from this step to this step, what we want to ask ourselves is, can we actually make this jump here? Can we actually definitively say that this limit exists and this limit exists so that we can make this step? In order to check that, we're going to kind of scroll over to the side here, do some scratch work, and figure out what we need to figure out for this problem. Okay, we're going to see if these limits actually exist on their own. So I'm going to leave some room here so I know what I'm writing down. So let's first evaluate the second limit. So let's evaluate the limit as t approaches 0 of t squared over sine squared of 3t. Okay, so we've investigated a limit of this similar form to this, right? We've kind of looked at the limit as x approaches 0 of sine x over x equaling 1, right? We kind of have that same setup in a way, but we're dealing with squareds and it almost looks like it's the reciprocal. In order to compensate for the fact that it's the reciprocal form of what we're used to, we have established before, we used it in the last video, that the limit of a reciprocal is the reciprocal of its limit. So namely, since if we were to have just t over sine of t at this point, since it's the reciprocal of this form, the limit of that would just be 1 over 1, or it would still be 1. Okay? So using that knowledge going forward, let's see what we can do to this function here to see if we can break it down at all to bring into play that whole limit of the reciprocal is the reciprocal of the limit. I think that what we can do first is we can split this function into the product of two fractions. Namely, and I want to kind of remind us of this here, we know that sine squared of 3t equals sine of 3t squared, right? We just kind of write this to make it a little bit more compact and succinct here, but this also means sine of 3t times sine of 3t. It has many forms. We commonly see it as this, but it also means these other two things here. So we're actually going to use this form here as we go forward to try to break this down a little bit. Let me undo all that so we have a little bit more room. Actually, let's go ahead and erase it. Okay, so now, and then we know that t squared is just t times t. So let's use these things that we just recently explored to see if we can break this down. We're not changing anything about taking the limit of two products here, we're just actually breaking down the thing we're taking the limit of. It's more of an algebraic step than a calculus step. So we get this over this. And once we get to this step, we've seen this kind of process before, but it's almost been flipped on its head, right? We've been using the reciprocal form of this. But in order to use that special trig limit and the limit of the reciprocal is the reciprocal of the limit, it's a tongue twister, I'm sorry. But in order to use that, we have to make sure that the same thing that's in the argument of our trig function is what's represented on the opposite part of the fraction. So in order to do that, we're going to have to multiply this first fraction here by a factor of 3. And when we do that, we have to compensate by multiplying the denominator by a factor of 3. And then we're also going to have to do that in the same sense for the second fraction. because they're both writing the same thing, but we need to make sure that we bring a 3 into here as well as bringing a 3 into here for multiplication purposes, right? And so since multiplication is commutative, what we're going to do is we're going to take this bit by bit here. This first 3, we're going to bring it in there, and that second 3, just like we said, we're going to bring it into the second one. So let's write down what we've got going on here. So we have the limit as t approaches 0, 3t over sine of 3t times 3t over the sine of 3t times, again, we're left with this 1 over 3 times 3, or 1 over 9. So now once we get here, we have the same thing in the argument of our trig functions as we do in the opposite halves of our fractions. So we know by using that special trig limit, and the reciprocal of the limit is the limit of the reciprocals, we can use that to know that both these limits exist, and we can use the product law to take them individually. So we have this times the limit of the same thing written again, times 1/9. So that and that, just to kind of fence it off, say what we're taking the limit of. So we know that this evaluates to be 1. Same story for that second one, and that's times 1/9. So this actually, the limit of t squared over sine squared of 3t as t approaches 0 is 1/9. So using a trig limit that we already know a couple times here and some different types of manipulation, we are able to show that the limit for this does exist. So we've taken care of one part of our question. Can we use the product rule for limits here? And we can on the second part, but we still need to make sure that this exists. And you may have noticed that earlier on in the video, I did write down something that looks like this, to where we know that as long as we have the same thing in the argument that's in the opposite side of our fraction, this limit does exist. But what I'm going to go ahead and explain in this video is I'm going to show you why this actually works and behaves the way it does. So for convenience sake, we do know this limit exists here. So we can use the product law, and this step is perfectly fine and just. But what I'm going to go ahead and do next, and I'm going to scroll down and do it down here, we're going to show why this limit works the way that it does. Okay, so we're going to stick to the script of our problem and write what we had originally. So we had the limit as t approaches 0 of 1 minus cosine of 11t over 11t. So for simplicity's sake, and kind of making a reference to what we did last section, we're going to make a substitution here. We're going to let u equal 11t, just to a little bit of shorthand and ease on ourselves here. So to complete our substitution here, we also have to note that as t approaches 0, u also approaches 0. Okay, so this limit, after we do our substitution, becomes the limit as u approaches 0 of 1 minus cosine of u over u. So this will more closely represent the form that we were more readily dealing with, something like this, right? So now, why does this limit equal 0? So let's do a little bit of asking ourselves this question. Can we plug in 0 for our variable we're evaluating and get our answer? The answer is no, because on the numerator we get 1 minus cosine of 0, which becomes 1 minus 1, or 0, and we get 0 over 0. So we get an indeterminate form, and so that leaves us to doing some more algebraic and calculus manipulation about these problems to see why our limit behaves the way that it does. What we're going to do, and I use this next vocab term very loosely because it's not actually the same thing, but it's the most easily recognizable way to take care of this problem. We're going to almost multiply the numerator and denominator by the conjugate of our numerator. I say that very lightly because it's not the same thing. We are not dealing with the same premises that we've done before with the conjugate, but namely what we did was we multiplied by a specialized form of 1 and we changed the sign. So it's very similar to multiplying by the conjugate, but it's also very different in the same breath. So don't go around broadcasting that we say it like that, but that was just a way to kind of help you recognize what we were doing. So now we're going to actually do this multiplication and see what happens to it. So we get the limit as u approaches 0, and the numerator is a difference of squares. We get 1 minus cosine of u times 1 plus cosine of u, so that turns out to be 1 minus cosine squared of u. Over, and we're going to leave the bottom unfactored, namely a lot like we do with multiplying by the conjugate. We're going to leave it like it is for right now. So now, do we recognize what this is right here? 1 minus cosine squared of u? If you answered a trig Pythagorean identity, you'd be correct, namely sine squared of u over 1 plus cosine of u, right? So now we have this, and we're kind of asking what can we do from here? Well, remember that sine squared of u is the same thing as saying sine of u times sine of u, right? So let's rewrite this numerator in that fashion. Let's take care of what we have in the numerator and expand it out a little bit. So sine of u times sine of u over u times 1 plus cosine of u. And what we see here in the top and bottom of this fraction is we have two separate multiplications going on, so we can break them apart into two fractions of their factors to make a product. So what I mean by that is we get this sine of u over u times sine of u. Sorry this work's kind of looking a little crooked. I just noted this, so I'm doing that to everybody. We get this. Okay, so once we reach this step, we ask ourselves again, are we allowed to use the product law for limits here? Can we take this limit and this limit individually, know they exist, and multiply their limits together to give us the limit of this thing? The only real way to answer that is to check piece by piece to say, does the limit of this exist? Which we know it does. It's one of the special trig limits we've been dealing with, right? Spitting image of it. Limit of sine of x as x approaches 0 over x equals 1. So we know this first part exists, but how does this second part, how do we know it exists? What can we do there? We're actually going to use another law for limits, namely the quotient law. And what the quotient law says is that we can break this fraction up here into the limit of the numerator divided by the limit of the denominator, provided both the limits exist and the limit of the denominator does not evaluate to 0. We can't divide by some 0 number, right? So in order to check that this doesn't become 0, we're first going to ask, can we pass to the limit? Can we plug in this value that we're approaching into our limit of our denominator here and get something other than 0? And the answer is yes, because 1 plus cosine of 0 is 1 plus 1, or 2. And we know the limit as u approaches 0 of sine of u exists because it's 0. So this limit exists, and this limit exists, and this one's non-zero. So we can use the quotient law for limits to say that this limit exists. Okay? So we have that we can actually use the product law for our original multiplication that we were dealing with. So we get the limit as u approaches 0, sine of u over u, times the limit as u approaches 0, sine of u, 1 plus cosine of u. We know that that's a sound next step because we showed that this limit exists on its own and this limit exists on its own. So we can take this next step here. We can take the limit of the product to be the product of the limits. This first limit here evaluates to be 1, and this second limit evaluates to be 0 over 2, or 1 times 0, or 0. So the limit of 1 minus cosine of u over u as u approaches 0, or equivalently this form here, actually does work out to be 0. So knowing that, we know that the limit of this thing also exists. We've already checked this one. We don't have to worry about this one since it's a constant multiple. So we know that this step that we are kind of always talking about being in question here actually does work. This is a sound step. We're more than welcome to use it, and we're implored to do so. So now, let's take the limit of those things individually and see what we get. So we just evaluated that this first one is 0. The second one, remember we evaluated to be 1/9. So this is 0 times 1/9. And the second one, that constant's 11. So we get 0 times 1/9 times 11, or 0. So the limit of our original function, let me scroll back over here to show you what we did. So we started with the limit of t minus t times cosine of 11t over sine squared of 3t. We wanted to evaluate the limit of that as t approaches 0. Works out to be 0.